Hello friends, I welcome you in lecture number 4 on relations. In this lecture we are going to discuss another property of relations which is known as symmetric relation. In lecture number 3 we have discussed one property of relation and it is called reflexive relation, and we have seen that a relation R on a set A is called reflexive if this type of diagonal elements are present in the relation for all elements of given set A. Now in this lecture we are going to define symmetric relation. So this is also easy definition. We can say that a relation R on a set A is symmetric if for any two elements A, B in a given set A, if order pair AB is present in R, then order pair BA must be present in R. If AB belongs to R implies BA belongs to R. For A, B belongs to A, then relation R is called symmetric on a set A. So here it is not necessary that this AB must be in R, but whenever AB is in R, then we must have BA in R. For example, we can make the symmetric relation on this set, say 1, 2 and 3. Suppose I want to write a symmetric relation on this set, then suppose I am writing one element as say 1, 1. Then we know that if we change the order of these two elements in this order pair, then we will obtain the same element. Then suppose I consider this element 2, 3. So here 2, 3 is present in R, and if R is symmetric, then 3, 2 must be present in R. So if 2, 3 is there, then I must add 3, 2. Similarly, suppose I am writing say 3, 1, then I must include 1, 3. So this relation R is symmetric on this set because if we take any order pair in this relation and if we change the position of elements in this order pair, then this property is satisfied. AB belongs to R implies BA belongs to R. Here 2, 3 belongs to R, therefore 3, 2 is also in R. 3, 1 belongs to R, therefore 1, 3 is also in R. And if we change the order here, we will get the same element. Therefore this is symmetric relation on this set A. So definition is easy. A relation R on a set A is called symmetric if for every A and B in R, whenever AB belongs to R, then BA belongs to R. Here I have written whenever. It is not necessary that this order pair AB must be present in R, but if some order pair AB is present in R, then if we change the order of elements in this pair, then resulting element must also be present in R if R is symmetric. We consider this example. We are given the set A equal to 1, 2, 3 and we have to decide that which of the following relations on this set A are symmetric. So we start with this first relation. So here I start with this element 1, 1 belongs to R. If I change the order of these two, then I obtain the same element. Then I come here 1, 2 belongs to R, and if I interchange these two, I must have 2, 1 also present in R if R is symmetric. But here 2, 1 is not present. So we can write that here 1, 2 belongs to R, but 2, 1 is not present in R, where this 1 and 2 are from given set. For 1, 2 belongs to capital A, order pair 1, 2 belong to R, but order pair 2, 1 is not in R. This means R is not symmetric. If R is symmetric, then we must have AB belongs to R implies BA belongs to R for all AB belongs to A. AB belongs to R must imply BA belongs to R for all AB belongs to A. If this happens, then R is symmetric. So if we want to prove that R is not symmetric, we have to find out at least one pair, and we have to show that that pair is present in R, but if we change the order, then the resulting pair is not present in R. Therefore, this relation R is not symmetric. Now we consider this one. Second relation is given by capital S equal to this set of ordered pairs. So 1, 1 is present in S. If we change the order of these two, we will obtain the same pair. Then 1, 2 is present. If we interchange these two, we have 2, 1 that is also present. Then this is diagonal element 2, 2. If we reverse the order, we will obtain the same element for 3, 3 also. So this relation S is symmetric. S is symmetric because AB belongs to R implies BA belongs to R. This condition is satisfied. Third relation is T equal to this set. So we start with first element 1, 1. No problem. If we interchange the order, we get the same element. Then again I have 1, 2 here also. So if I interchange 1 and 2, I get this order pair, but that order pair is not present here. Similarly, we can check for this also. 2, 3 is present in T, but if we change the order here, then we obtain this pair 3, 2 that is not present in T, and here we should mention that 2 and 3 are in a given set. So this implies T is not symmetric. If our relation is not symmetric, then we have to show the existence of two elements such that this condition is satisfied. 2, 3 belongs to T, but 3, 2 is not in T for 2, 3 in a given set. Next one is empty relation. So empty relation is always symmetric because here we are not having this type of situation. Okay, there is no pair in empty relation. So if AB is in given relation, then we have to check whether BA is in given relation or not. But here this relation is empty relation, so there is no pair in this relation. Therefore empty relation is symmetric. If relation is not symmetric, then we have to show the existence of at least one order pair such that this condition is not satisfied. But phi is empty relation, so there is no such pair. Therefore phi is symmetric. Then we have universal relation. So universal relation means it includes all possible pairs. So whenever we have AB belongs to A cross A, then because it includes all possible pairs, BA is also in A cross A for all AB belongs to A, where A can take the values 1, 2, 3. Similarly, B can also take the values 1, 2, 3. So universal relation is always symmetric. A cross A is symmetric. Empty and universal relation are always symmetric relation. Similarly, we can talk about relations on the infinite set. Here it is written that the relation of less than or equal to is not symmetric on this set of real numbers. So this relation we can write as R equal to order pair AB such that this A and B are from the set of real numbers, and the relation is less than or equal to, that is A less than or equal to B. So this relation is not symmetric on the set of real numbers. So we can find out one pair which is present in R. For example, if we take A equal to 2 and B equal to 3 in R. Okay, for these two values, for A equal to 2, B equal to 3 in R, we have order pair AB equal to 2, 3, which is present in the relation because 2 is less than 3. But if we reverse the order, but suppose we find out BA, that is 3, 2. Now this is not present in R because 3 is not less than or equal to 2. Therefore, this relation is not symmetric. Therefore, less than or equal to relation is not symmetric on this set of real numbers or on R. The relation of equality is symmetric on the set of real numbers. We are familiar with the relation of equality also. We have to consider all ordered pairs AB such that A and B are real numbers and A equal to B. So here if we take any pair in this relation, suppose we consider for any two real numbers AB belongs to R. If we consider this ordered pair in R, then we can say that A equal to B, because if AB belongs to R, then it must satisfy the condition of given relation, and here condition is both are equal. So this we can rewrite as B equal to A, and therefore by the definition of given relation we can write that B comma A belongs to R because B equal to A. AB belongs to R if A equal to B, therefore BA belongs to R if B equal to A, and this A and B are arbitrary real numbers. So we have shown that if we take any two real numbers, then whenever AB belongs to R, then BA belongs to R. Therefore this relation of equality is symmetric on this set of real numbers. So this is also easy property of relation. We should remember this definition that relation R on a set A is said to be symmetric if for all AB in a given set, whenever AB belongs to R, we must have BA belongs to R. And if we want to prove that given relation is not symmetric, then we have to find out at least two values in given set A for which AB is present in R but BA is not present in R. So this is the definition of symmetric relation, and we have discussed several examples of symmetric as well as not symmetric relations to understand this definition, and we will continue with these properties of relations in upcoming lectures. Thanks for watching.